Hello, welcome to today's webinar focused on enhancing gas supply systems. Thank you for joining us. This is Pete Singer, editor of Semiconductor Digest, and today's moderator. We have two great presenters today, Alex Istrate, who's a system architect for sensor applications at TE Connectivity, and he's been there for over 6 years. Joining him is Vincent Wong, who is the engineering manager, also at TE Connectivity, and he's been there for almost a decade. So very well experienced people, and we will have a question and answer session at the end of the presentation. You can ask a question at any time, of course, then or during the presentation using the chat function at the right-hand side of your screen. It's a little chat button with a question mark in it. So please get your questions ready. And with that, please welcome Alex and Vincent.
Hello and welcome. I'm Alex, and together with my colleague Vincent, we'll talk about gas supply systems in the semiconductor industry. Now, before we proceed, I want to thank our host, as we're very excited for this opportunity. So let's get started. Looking at our agenda, we want to walk you through some of the main topics for today's presentation. We will start by describing the ecosystem of gas supply systems, where we will look at a typical system diagram, and we'll highlight the main building blocks as well as its key features. We will explain how sensors are an essential part of the systems, and we will dive into the main characteristics related to ultra-high purity and how this can be achieved. We will continue by explaining what are the top requirements when it comes to sensor application in this field, and what are necessary technologies to fulfill these. Finally, as Pete was mentioning, we'll allow enough time for a Q&A session at the end of the presentation. Now, before we dive into the gas supply systems, I'd like to present some of the key facts and figures about TE and Sensors business unit. TE Connectivity is a global industrial technology leader, creating a safer, sustainable, productive, and connected future. Our broad range of connectivity and sensor solutions, proven in the harshest environments, enable advancements in transportation, industrial applications, medical technology, energy, data communications, and the home. With more than 85,000 employees, including over 8,000 engineers, working alongside customers in approximately 140 countries, TE Sensors is a part of the connectivity, and therefore a world leader in sensing solutions. We're providing sensor technologies in 11 countries with a team of approximately 700 engineers. Last year, we have achieved $1.1 billion in revenue, with approximately 80% from harsh environment applications. Now let's have a closer look at how a gas supply system looks like. So let's start from what is the main purpose of the gas supply system in the front-end semiconductor wafer processing. That is to store, distribute, and deliver specialty process gases in a safe, controlled, and precise manner, while unaltering the intended chemical composition and physical state of the fluids. In this case, the fluids referred to are specialty process gases of ultra-high purity grade, which is a topic that we will explain in further detail in the following slides. So continuing on the three aspects mentioned earlier, safety, control, and precision, safety is a fundamental requirement since these types of gases are often hazardous and harmful for the personnel working in that environment. And leakage can lead to very negative consequences. Control over the entire supply process is necessary to achieve efficiency and yield targets, which are critical for the successful operation of foundries. And last but not least, precision, which we will refer to as accuracy, repeatability, and stability of the signal outputs provided by the devices such as sensors or other instruments which are participating in the monitoring and regulating the delivery of the gases. With this understanding in mind, we can now describe the system and its diagram shown on the screen. The main building blocks of a gas delivery system are gas cabinets, located usually in a well-designated area, so-called gas room, valve manifold boxes located in the subfab, and integrated gas systems, also referred to simply as gas panels, which are located on board the equipment inside a clean room environment. We will now dive into each one of them individually. Gas cabinets, as the name describes, is the place where the source of gas is located, and usually there are separate cabinets for each type of gas. Currently, there are more than 100 types of gases, and as more advanced process nodes are developed, new and often exotic chemistries are required. Inside a gas cabinet, typically there are 1 or 2 cylinders of the same specialty gas type, and in some cases, an additional cylinder of inert gas, which is necessary for regular purging operations. In other cases, inert purge gas is readily available on site. Gas cabinets have the purpose to ensure uninterrupted, regulated flow of gas and to guarantee safety during storage. This means it has a series of mechanisms in place to prevent any risks such as gas leak and flame detection, overpressure relief, interlocking access control, exhaust and ventilation. Through a series of valves, switches, and sensors, and other automation features, the cabinet will constantly monitor the gas pressure at the source in each of the cylinders, which is achieved by the use of pressure transmitters, sometimes up to 10 per cabinet. And it will regulate the output pressure towards the VMBs. It will monitor the level of the fluid inside the cylinders, and that usually is done by the use of a scale. And that's usually one for each type of cylinder. It will also switch between the available cylinders to ensure continuous supply, and it will execute purging cycles when necessary. The main role of a sensor in this case is to provide accurate, repeatable, and stable signal output in all conditions, as well as reliability, which will enable a longer and uninterrupted operation of gas cabinets and a high usage of available source gases. In our next slide, we will explain more about VMBs, which will have the role to take that incoming gas and distribute it evenly across multiple gas lines, which is achieved by a series of manifolds, valves, and pressure regulators, as described on the picture on the left. Gas pressure is monitored continuously by an individual pressure transmitter located on each outgoing gas line. VMBs have the same safety requirements as the previously described gas cabinets and therefore have similar safety features. As wafer capacity increases, the number of process tools will drive the need for more VMBs, and this leads to VMBs being used in sequence, since this can only host a limited number of individual gas lines, often up to 10 gas sticks. In this case, the role of sensor is very similar to what was previously explained, and that is to enable a longer, uninterrupted operation by having accurate, repeatable, and stable output in all conditions. VMBs will also regulate downstream pressure one level further before the ultra-high purity gases will reach the point of use, which we'll cover in our next slide. This is the integrated gas systems. And these are modular assemblies, also called IGS, or simply gas panels, which are located on board with the process equipment within the clean room environment and constitute a collection of individual gas lines of various process gases. Each gas line, referred to also as a gas stick, typically contains manual and pneumatically actuated valves, a mass flow controller, and depending on the design and tool requirements, it can also have a pressure regulator and a pressure transmitter. The IGS allows the accurate controlled flow of multiple gases according to a specific recipe for a given wafer process. Modern gas panels have transitioned from welded or face seal fittings to surface mount type fittings, which enables them to be approximately a third of the initial size and thus allowing a compact form factor for an easier integration into the equipment. This also shortens significantly the flow path length. Mass flow controllers are the devices necessary to precisely regulate the flow of ultra-high purity gases, and these are generally divided into two main types, based on the operating principle for calculating mass flow. Thermal-based MFCs, using a heat transfer principle, and pressure-based MFCs, typically relying on differential pressure measurement. More advanced thermal MFCs typically use at least one pressure sensor, which is generally used to remove any effects of fluctuations in the upstream pressure. On the other hand, pressure-based MFCs will use pressure sensors to measure pressure before and after a laminar flow element or restrictor to calculate mass flow. As before, reliable, accurate, repeatable, and stable sensor signal output is crucial in achieving repeatable execution of complex process recipes and high processing yields. Now, on the next slide, we'll present what defines an ultra-high purity grade gas. It defines its chemical composition, purity, and delivery. It is estimated that up to 20% of yield losses are attributed to chemical contamination. Regarding purity level, which is one of the most important aspects, the requirements in industry are extremely stringent, being higher than 99.9%, often referred to as 5 nines and above, which describe how many nines are after the comma. In other words, the impurities contained are in the order of parts per billion or even parts per trillion level. It's important to note that this varies based on the type of gas and the type of process. Achieving these high levels of purity involves rigorous gas purification processes, filtration, and extensive quality control measures throughout the entire gas supply chain, from production to delivery to the semiconductor fab. Additionally, specialized gas containers in delivery systems are used to prevent contamination during transport and usage. The other aspect, why ultra-high purity grade gases are necessary, the answer is because it is essential to ensure reliable and precise manufacturing of semiconductor devices. As mentioned earlier, contamination is one of the main risks and can come in various forms. The most common one is corrosion, which can be generated either by chemical reactions between the materials used in the construction of the systems and the process gases, or by the presence of moisture. The byproducts of such will have consequences on the surface of the wafer, which are likely to lead to yield losses. Another reason is in fact a phenomena where the molecules adhere to the surface due to its intrinsic porosity. This is called adsorption, and even if the effective quantities are very small, down to molecular level, the risk is that the same molecules can be released at any time, which can lead to an unpredicted event, and ultimately affecting the process negatively. This is linked to the previous point where there are unwanted chemicals entering the process chamber. Typically, delivery systems have a few ways to mitigate these risks by using filters and by nitrogen purge cycling. However, these particles are used to maintain the purity rather than achieving it. To achieve the necessary purity levels, the system will be designed having the following considerations: using the adequate materials, having the adequate surface finish, ensure no chemical buildup in dead volumes, having the necessary fittings to ensure leak integrity, and finally, cleaning and preserving this during manufacturing, transportation, installation. In the following slide, we will dive deeper into these details, and it is my pleasure to hand over to my colleague Vincent, who will guide you through the next part of the presentation.
Thank you, Alex. We can look at the requirements of sensors in gas supply systems through three pillars: ultra-high purity, high reliability, and accuracy and repeatability. Under ultra-high purity, our sensors are built around the capability to use wetted materials like 316L VIMVAR and C276 nickel alloy. The wetted surfaces can be electropolished below 5 RA and are tested against semi-inspection requirements. We offer a wide range of sealing types, from surface mount to VCR to custom weldments of adapters and manifolds. Under reliability, our sensors are rated to maintain performance after 1 million pressure cycles. We test our sensors against challenging conditions seen in gas delivery systems like overpressure and long-term vacuum conditions. Lastly, we're industry proven. We're in over 1 million sensors in gas delivery We're in 1 million gas delivery systems in the field. Under accuracy and repeatability, our mid-pressure sensors can maintain 0.1% accuracy, and for the lower pressures, 0.5%. In long-term stability, our sensors are typically change less than 0.1% span per year. For enhanced performance, we offer custom temperature compensation as well as digital and analog output. In the next slide, we can discuss more about sensor performance. In the gas delivery systems discussed earlier by Alex, the gases in the chamber create features and layers that are critical to the performance of these semiconductor devices being made. So it is important to maintain a precise and stable pressure of the gases used in these processes. Pressure transducers are used to measure the delivery of the gases in these systems. If the transducer exhibits long-term drift, the measurement will be gradually changing over time, which can lead to errors in the process and defects on the semiconductor wafers. Ultimately, a more stable sensor gives extended service life, less downtime, and enables higher levels of performance. TE holds in-house MEMS design and manufacturing capabilities of these sensing elements. As such, we can tailor our designs for the performance needs of our targeted applications. Below are plots from an accelerated stability test of 1 psi oil-filled pressure sensors. We currently have good stability against our competition. but we're developing a next generation product with class-leading stability, which is set to launch early 2024. In the next slide, we can delve more into the working principles of pressure sensors. One slide back, please. There we go. So the piezoresistive effect is a change in electrical resistivity of a material when mechanical strain is applied. The change in resistance is due to the change in the material's crystal structure, which affects the flow of electrons through the material. The band structure describes the range of energy levels that electrons have within a material. The piezo effect is more pronounced in semiconductor material like silicon, as the band structure can be arranged to be more sensitive to strain. Silicon piezoresistive pressure sensors allow for higher sensitivity, higher overload because of lower strain levels, and with developed MEMS processes allows for a miniaturization of devices. TE applies this in two sensing technologies, strain gauge and pressure die. With these two technologies, the resistors are typically arranged in a Wheatstone bridge configuration to output the changes in voltage. In the next slide, we can discuss more about the strain gauge technology. The key components to a strain gauge pressure sensor is first, the silicon piezoresistive strain gauge. Also, we have the pressure port and an intermediary glass bonding layer. In the construction, the pressure port and its diaphragm are machined out of one single solid stainless steel block of material. Silicon strain gauges are attached in strategic locations to the diaphragm using a special glass process at high temperature. As shown in the diagram on the right, as pressure is applied through the sensor port, the strain gauges deform and the diaphragm, they deform with the diaphragm and the resistance changes accordingly. The key features and advantages of this technology is that the robust design allows for very high pressure. Secondly, there are no welds or O-rings, so there's no concern of internal leaks. The ports can easily be machined into a wide range of threaded interfaces. 316L VIMVAR can be offered as the wedded material. And finally, the construction is simple and cost efficient. In the next slide, we can talk about our second sensing technology. So pressure die and oil-filled capsules. The key components to this are the silicon piezoresistive die, metal diaphragm, metal sensor body, and silicon oil. The construction of the pressure die shown in the upper left consists of a silicon membrane and resistors which are implanted onto this membrane. As strain is applied to the membrane, the resistance changes. Depending on the design of the die and the processes used, often a constrained wafer is bonded to the silicon for mechanical support and stability. To make this sensing element device compatible with the widest ranges of gases, the pressure die is bonded into a metallic sensor body. A metal diaphragm is then welded to the sensor body, creating an enclosed volume. This enclosed volume is filled with silicone oil and then sealed with a resistance weld. With this assembly, pressure is applied to the metal diaphragm. The diaphragm flexes in reaction to the applied pressure, and then the silicone oil transfers the pressure to the pressure die. With the strain applied to the membrane of the pressure die, resistance changes. The pressure die is completely isolated from the pressure gas media. Key features and advantages of this technology. This type of technology has very high sensitivity, with pressure ranges going all the way down to 1 psi full scale. Secondly, the pressure die offers very high levels of accuracy and stability. Wedding materials for this can be either 316L stainless steel or C276 nickel alloy. Finally, the welded assembly has very high burst pressures. And with that, I'd like to bring this discussion back to Alex to introduce more of the TE portfolio.
Thank you, Vincent. We want to offer here a snapshot of our capability in the space of the industry, and we will highlight some of the main features and differentiators. For our pressure products, we are entirely vertically integrated from the core sensor element, which relies on the technology and features described earlier by Vincent, all the way to the finished and ready-to-use product. Our pressure capsules rely on some of our most advanced pressure dies, where TE, with its capability to innovate, enables superior stability and accuracy in a wide pressure range while reaching a high proof and burst pressure rating, both of which are necessary for the applications described earlier. Products such as the MOL 85 are a very good example of refined packaging for ultra-high purity media compatibility with a compact form factor, which makes it easy for integration, as for example, into mass flow controllers, pressure transmitters, or any other devices which involves pressure measurement in low pressure ranges, such as below 30, 15, or even down to 5 psi. Those are the components you can see on the left side of the screen. These pressure transmitters can rely on both types of sensor elements, strain gauge glass bonded onto the pressure port, typically used in higher pressure ranges, or on the media isolated capsule containing our advanced MEMS for the low pressure range. This can be configured with a variety of connector options and industry-specific fittings, such as the conventional welded versions, swivel face seals, as well as the W and C seal surface mount types. We also have the capability to offer both analog and digital compensated signal output, either by the use of laser-trimmed resistors on the PCB placed on the back of the sensor, or with our in-house designed ASIC portfolio, which was designed and developed to work perfectly together with our MEMS dies. Our load cell are a perfect fit for applications in cylinder scales where high overload protection is necessary. And our thermal pile broad offering in various packaging types, as well as integrated modules, can be used in the infrared spectrum sensing applications for flame detection, for example. And on the final slide of this deck, we want to provide a recap of what has been presented by myself and Vincent. So sensors are key for unlocking enhanced reliability and performance in gas delivery systems. TE has a comprehensive sensor portfolio for gas delivery applications in pressure, temperature, and force, with deep expertise in design and manufacturing sensors for the high purity market. Our focus is on stability and repeatability, which allows to reduce downtime and extend equipment reliability. We partner closely with our clients to create integrated solutions that cater to the complexities and integration challenges in chemical supply systems. We're excited to be developing leading-edge solutions to enable new processes and technologies, and TE Connectivity is a commitment to ongoing innovation, ready to meet the future challenges in chemical supply systems. With this, we have now covered all the slides, and before we continue, just a small reminder on the fact that at the end, everybody who registered for the webinar will receive a copy for the presentation and the link to the on-demand recording. You'll also receive information on how to connect to an expert at TE. So thank you for listening, and now we can open the Q&A session.
Okay, well, thank you, Alex, and thank you, Vincent. We have indeed reached the Q&A portion of the webcast. And as a quick reminder, you can easily ask a question. Just go to the chat function at the right-hand side of your screen, and you click on that and you type your question in. So let's see, we have some questions already. And the first question is, what are the limitations of current strain gauge technologies in measuring pressure, and how does TE Connectivity address those?
I can take this one. So one of our goals for the strain gauge based sensors is to extend into lower pressure range offerings. We see more and more applications where 10 or 15 psi is the full scale range. Our MEMS designers have recently completed a new strain gauge design with enhanced stability. We're excited to implement it and explore what new capabilities we can enable with such designs. Thanks for the question.
Okay, perfect. And another question is, how do you mitigate the risks associated with oil capsule rupture in ultra high purity systems, given that even trace amounts of oil can be detrimental to maintaining ultra high purity?
Sure, I can also take this one. If we can go back to the slide, I think it's slide 14, where we show the oil fill capsule assembly. Yeah, this one right here. So you can see in an absolute pressure configuration like the one you see here, oil is fully contained by welds. The metal diaphragm is TIG welded, the lower portion is resistance welded. All of these welds are qualified for pressures in the thousands of PSIs, which are generally over the normal pressure ranges of instrumentations seen in gas delivery systems. So the oil is well contained and then rated for the application. Thank you. Thank you for the question.
Okay. Well, actually, those were the questions that we had. Oh no, hold on. Wait 1 second. The question is, what test standard are you using for performance evaluation? Are you using SEMI F113?
Yeah, we have a number of qualifications that we apply. Depending on the industry, SEMI is one of the ones that we consider in the design and qualification of these specific sensors.
Okay, very good. Well, I think that answered all the questions. So with that, let's unless you have any concluding remarks, we can wind things up. Okay, well, thank you, Alex, and thank you, Vincent. Thank you, audience, for joining us, and we look forward to future webinars.
Thank you.
Thank you.